today what we will try to do, we will try to argue that for a particular case, which is NF is equal, so as you remember that Affleck, Dine and Seiberg, they gave a superpotential W just based on the arguments of holomorphicity and R charge. So just based on these two arguments, they proposed some superpotential for the cases when the number of flavors was less than the number of colors. So today what we will argue that for the particular case when NF is equals to n minus 1, this superpotential can be derived from the from instanton effects. Okay, so before going into that derivation, I'll review, I think most of the part of the lecture is about review on instantons. So I'll review instantons. If I'm going too slow, let me know because anyway. So, okay, so what are instantons? So instantons are the configurations of finite are the Euclidean are the configurations whichever finite Euclidean action, and how let's say we are working with SUN gauge theory. For the moment, let's say it's just, it doesn't have a supersymmetry, it's just the action is integral d for x f mu nu is a trace so of the color index 1 over 2 g square. Now what I can do, I can express this action in the following way. So I can basically write it as f mu nu plus star, where this is the Hodge dual. So f mu nu star of f mu nu is half epsilon mu nu rho sigma f rho sigma. We are in Euclidean, so I am not distinguishing upper and lower indices. So f mu nu square. So I can write this because I will get one term which is f square, other term which is star f square, which is same as f square, and the other term is 2 f star, which I am either subtracting or adding depending on whether there was a plus sign or a minus sign. So you can write it in this way. Now this is positive definite. So therefore the action is bounded. And the bound is basically you will get plus minus 1 over 2 g square trace of f mu nu star f mu nu. And as many of you know, sorry. As many of you know that this is just a boundary term. It's basically a mu's plus 2 by 3 times the a mu thing. So now we also want action to be finite in an instanton configuration. No? So that means f should go as 1 over r square at r goes to infinity, because there is a d4r. So therefore a should go as 1 over r as r goes to infinity. So a should be basically approaching 0 at large distances. So at the boundary, because this is a boundary term, I want to know the boundary value in a sense. So at boundary, this a mu just becomes a pure gauge configuration. There's a I. And when a mu is this term, when you, this is a d4x, then that will become just a boundary integral, and this term just becomes 8 pi square over g square k, where this k is an integer. Now in the case when f was either star f mu nu or whether f was dual or anti-self dual, that is f mu nu was whether it was star f mu nu or f mu nu was minus star f mu nu, this, this equality is saturated. So in that case, the action is basically 8 pi square over g square. Okay. So this is so such configurations are called instanton configurations. So this is instanton, this is anti-instantons. For this k is 1, this is k minus 1, but there's a mod k that appears in the action. And the value of the action in an instanton configuration is basically this. Yeah.
And maybe you can pause now.
Yeah.
Does everyone understand why the integral of the instanton is an integer?
It's like a Chern-Simons term. It's the number of windings.
Number of windings. So let's just say that clearly, as Diksha said, at infinity, the Cree configuration must become pure gauge. Because if it wasn't pure gauge at infinity, we would get infinite action.
Yes.
Okay. Therefore, but infinity is an S3. Because there are many directions you can go to infinity. So what you have is a map from S3 to the gauge map.
Yes.
Now let's take the simplest case of SU2.
Yeah. So SU2 is basically S3. So there is a map from S3 to S3, and these maps are integers. So usually when people write as Z, okay, I don't want to, yeah, Z of S2 of SU2 of S3 is an integer.
Exactly. And you can see that this is an integer. One way of seeing it is that when you write down that f wedge f, you see it's just a Jacobian of it. You've got one S3 to another, and then that f wedge f turns into that Jacobian. So it tells you how the ratio of volumes. It's signed volumes.
Yes.
So how many times it's wrapping around? Okay.
Yes.
So and this thing that we saw for SU2 as a generalization is also true for SUN.
SUN. Yes.
It's harder to see because group manifold of SUN is a more complicated beast. But the point is the group manifold of SUN also has non-trivial 3 cycles.
Yes.
I think the only general group, the third fundamental, the third moduli group is Z.
Yes, is an integer.
I think that's right. And roughly speaking, it's all happening within an SU2 subgroup. So though we worked it out for SU2, we don't lose much.
Yeah.
You know, the basic intuition we got there.
Yeah. So even when I'll write down instanton configuration, I'll write for SU2, but for the higher dimensional one, what you can do, you can have that SU2 block diagonal, and then the rest of the things just go along for the right.
Where that SU2 points
Yes.
in the group.
That gives you one more moduli. Yeah.
Yes. And one or two more things. Notice that Diksha argued that this f self-dual squared is positive. Now, may seem like an obvious statement, and of course it is an obvious statement, but notice that it's only true because of the Euclidean.
Yes.
Because otherwise this inner product, this thing. So this manipulation sort of is importantly.
Yes. Yes.
And should F go less than
Faster.
Faster than. Yes.
Into some S3, non-contractible S3 in that group. Okay, so just like, suppose you had a circle, map from a circle, and you had some other manifold, let's say S3 times S1. Being a trivial example. S3 times S1 is a 4-dimensional manifold, but it has a non-contractible 1-dimensional cycle. And then your string can map around that S1.
Yes.
Okay? You can have more non-trivial examples. What you need is a non-contractible
S3. Yeah. Okay. And it's also easy to see that these configurations, the instanton configurations, satisfy equation of motion. Because we were looking for solutions of equation of motion which give a finite action. So how? Because let's say if I take this example, so the equation of motion is del mu f mu nu is equals to 0. But since f mu nu and f mu nu star is same, this is just the Bianchi identity. So this is automatically 0.
And that's the algebra. And logically speaking, it had to, because it's the minimum energy,
Yes.
the minimum action configuration subject to a conserved charge. Therefore, it extremizes action.
Yes. Okay. Okay, now let's focus, as we said earlier, let's focus on SU2 case. Because higher dimensional cases are analog of this, it will have just more moduli as compared to SU2. So for SU2 case, so usually what one does is, in order to find instanton solution, one puts an ansatz for A mu and then you try to find out the parameters using this duality, self-duality or anti-self-duality equation. So I'll just give you the solution. So for SU2, A mu is basically sigma bar mu nu x minus A nu over x minus A whole square plus rho square. So notice there are a lot of parameters here. Let me just write what are sigma bar. So sigma bar mu nu, okay, sigma bar mu nu is basically half sigma bar mu sigma nu minus sigma bar nu sigma mu, where sigma is the Pauli matrix is sigma I times identity. The fourth component is identity, and sigma bar mu is sigma I and minus identity. So as I defined sigma bar, you can define sigma mu nu also. So sigma mu nu will be half sigma mu sigma bar nu minus sigma nu sigma bar mu. And the nice thing about these matrices are that sigma bar is automatically self-dual. So some of the properties which are useful, sigma bar mu nu is half epsilon mu nu rho sigma, sigma bar rho sigma, and similarly sigma mu nu is anti-self-dual. So minus half epsilon mu nu rho sigma, sigma. So, okay, so this is the configuration A, but notice that in this configuration there are a lot of parameters, and what these parameters tell you. So this A is telling us about the location of the instanton. So these are 4 parameters which are related to the location of the instanton. Rho is telling us about the size of the instanton. So there is this one parameter, and also I could have applied the global part of the gauge transformations onto A mu to get new configurations. So that gives us 3 more parameters. So given a A mu, oh sorry, this SU2 case with k is equals to 1. So I am always looking at the instanton charge, which is 1. So given this A mu, one can find what is the F mu nu, and it's easy to show using the properties of these sigmas that F mu nu is self-dual. So F mu nu for this case is sigma bar mu nu rho square over x minus A square plus rho square square. So some things which we should note, this goes as 1 over x as x goes to infinity. So if A mu is a function of x. And this goes as 1 over x square. This is what we had also demanded, that it should, yeah, sorry.
What about the answer to Chintan's question? Shouldn't it have gone faster than 1 over x square? How is it finite if
Yes.
it doesn't go like 1 over x to the 4?
No, sorry. F mu nu goes as x square. F mu nu is x4.
Is it in your expression?
Oh, sorry. It's x4. Sorry. There was a square also. Sorry. Yeah. So it goes as x4. Yeah.
I mean, despite the fact that A goes like 1 over x, because largely that 1 over x piece is purely h.
Yeah. So basically, F mu nu is this, no, del mu A nu minus mu goes to nu plus A mu A nu. So you have to compute this, and yeah, there is a square because of the when you take derivatives you will find this happens. So okay, so now let's talk about the parameters which are there in the solution. So there are, as I said, there are 4 parameters which are A, which tells you about the location of the instantons in the space. Then so this is corresponding to location. Then there is one parameter which is rho, which is corresponding to the size of the instanton. And then there are 3, because it's SU2 parameter, which is telling you about the gauge, global part of the gauge group, how it's embedded in the gauge group. So these parameters are called the moduli space. So why they are called moduli space parameters? Because if you change these, the action will not change. So it will give you a new instanton configuration with the same action. Because the action is just dependent on k, and I have fixed k to be 1. So these are also called zero modes. Zero modes are the configurations which are the fluctuations around a mu, which when you change those parameters, the action doesn't change. And you can understand these zero modes as basically Goldstone bosons. How? So a mu, when there is a special A, it's breaking the translation symmetry. So these are the 4 Goldstone modes corresponding to breaking of the translation symmetry. This is one because remember f mu nu in 4D is conformal, because if you scale, so this is breaking that scaling symmetry, the one Goldstone boson, and these 3 Goldstone bosons are due to breaking of the global part of the gauge thing. So, yeah.
So, notice something interesting. Maybe you're going to say this to each other. I don't know if you're going to say this to me, but no, first let's look at the logical structure of that. Sigma in that thing is a 2 cross 2 matrix. Because SU2 gauge fields are 2 cross 2 matrices. If you want the 1, 2, 3 components of the gauge field, you take the coefficient of sigma 1, sigma 2, sigma 3. That sigma bar mu nu there is a traceless matrix. So it can be expanded in sigma 1, sigma 2, sigma 3.
Yes.
Now, from this point of view, the 1, 2, 3 indices are indices of where you are in the gauge field.
In the gauge, yes.
But x nu in x minus a mu is an index of where you are in space. And notice that we've got a dot product between an index of where you are in the gauge group and where you are in space. Notice that this configuration is not invariant under rotations in space alone.
Yes.
Because if you rotate it in space alone, then x minus a moves like a vector. Okay? Even if you rotate a, it's not invariant under rotations in space alone.
Yes.
It's not invariant under rotations of gauge group alone. But there is one combination of the two. Namely, identifying gauge group
With the rotations.
Note both are ISO3s. Okay?
If we then go to some other gauge group, then
You still rotate in an SU2 subgroup.
Yeah.
Okay? So it's always like this.
So that's why rotation don't have extra.
Yeah,
Yes.
so whether you want to call this a zero mode due to rotations,
Or the gauge.
gauge group is up to you. There were two things. There was an SU2 times an SU2. It's invariant under one linear combination of them,
Yes.
but not the other one. It's got this color space locking. This
Yes,
configuration. It's a very beautiful feature.
Yeah.
And it's SO3 not SO4 because there is scaling. They're in 4 dimensions.
Right.
Yeah, the boundary is SO3.
Boundary is SO3. That is.
So this is,
No, but the rotation group. Well, I suppose what's going on here is that it's invariant.
so SO4 can be written as SU2 left, SU2 right, and there is this SU2. So it's invariant under, I think, the diagonal subgroup. The diagonal subgroup of SU2 left, SU2 right maps to the gauge group, the way as Shiraz was saying, and hence there are 3 due to the broken ones.
Then what happens to the remaining Lorentz transformations?
Remaining Lorentz transformation, so it's,
They will change the instant.
no, so this transforms like a vector under Lorentz group, no? Mu, there's a mu index, which a mu should transform as a vector. Yeah, the location is breaking translation. You are asking about boost, okay, the translation and rotations.
Not boost, but you said that it's a subgroup of, so this interlocking is happening in the subgroup of the
Yes, right.
Lorentz group, right?
Hmm.
But there is a remaining part of the Lorentz group. Will that change the instanton configuration and correspond to more parameters?
You're saying only a subgroup is broken, not the whole thing is broken.
Yeah, if it was that only a subgroup was broken, that's good. Because if it's invariant under one of the SU2s, the rotation in that does not generate anymore. It's only the broken things that.
The Goldstone modes are corresponding to the broken symmetries. So,
Right?
yeah.
So one SU2, so I think it must be that out of the 3 SU2s, as you correctly said, one of the SU2s is broken. I can't see the details in my head.
Okay.
So one diagonal SU2.
Yeah.
Preserved, one some off diagonal is broken, and the third SU2 by itself is just preserved. Must be. We can work that out after.
Okay, now the next thing which we will need, so in order to derive this Fleck-Dine-Seiberg superpotential, we will need 2 things about instantons. One are how many zero modes are there for that instanton, and the other thing is the metric on the space of moduli space of instantons. So I'll explain both the things in this non-supersymmetric case, and then we can go there. So first is like counting the zero modes. So these are the zero modes. For example, in this SU2 case, there are 8 zero modes. So yeah. So all these things will give you a different instanton configuration, but the action is still same. So that's why they are the
Because
zero
they're
modes.
generated by a symmetry, action of a symmetry. It will not change the action. As Diksha said, think of it like Goldstone. If something is broken, then that broken thing will be rotated.
Okay. So if I have to count the zero modes, what do I have to do? So let's say A mu is some general configuration. I can write this as A mu classical. Classical is the, okay, I shouldn't have used classical word, but okay, it's basically this answer. And then I want to look fluctuations around these solutions. And these fluctuations have to be such that they are still instanton solution. That is, if I write down a field strength for delta A mu, which is basically d mu delta A nu minus d nu delta A mu, it should be the dual of the corresponding thing. It should be the, so I want that the fluctuations are such that you are still in the instanton solution. So the fluctuations satisfy self-duality or anti-self-duality, whichever the solution this was. And the other thing we want to demand is that these fluctuations are not just trivial things. Trivial things are the ones which are basically A mu. If I just do a gauge transformation on A mu, I get a new configuration, but that's related to the original one with just a gauge transformation. So I don't want these fluctuations to be such that they are related to the original solution by the gauge transformation only. So the second condition you demand on this A mu is that it's perpendicular to the gauge transformations. So that is basically if I want d4x trace of d mu lambda, lambda is the gauge rotation, A mu is equal to 0. So it's orthogonal to the gauge rotations, so that when you get this new configuration A nu, this new configuration is not related to the old just by the gauge transformation. So I want to count these numbers. So this thing I can do an integration by parts, and I can represent this as d mu of delta A mu is equals to 0. So these are the 2 conditions which I want my fluctuations to obey. One is this condition, one is this condition.
Sorry, can I say one more thing about the earlier discussion?
Yes.
Suppose you look at SO4, the rotation group SO4, and you consider a vector. Okay. Now we can ask, what is the stabilizer group of that SO4, that vector? That stabilizer group is SO3. So a vector, if you turn on a vector, it does not break all of SO4. It breaks that part of SO4 that is not in SO3. So there's a vector preserves one SO3 subgroup. So that's what's happening there. You see the solution has a vector in space. So SO3 is preserved. It's the remaining part that's broken. That's exactly what we said, right? One of the rotational SO3, actually some diagonal of the 2 SU2s,
SU2s, yeah.
is preserved. The thing that's broken is the off-diagonal that lets you use. And that guy
Gives you the zero
combines
modes.
the gauge. Right? There's one combination of that plus gauge which is also not broken.
It's the broken thing which corresponds to collective.
Collective, yes.
Okay.
And teacher, just one. This capital D is when derivative with respect to
Yeah, with respect to this. So I should have written this. So this capital D is in the old background. So you have to work order by order in perturbation theory, no? So when you do this, so actually this one can see just from the Lagrangian. So my Lagrangian was F mu. I transform A mu as A mu plus delta A mu. Then what I will get is first will be the old one which I am calling classical, F mu classical, F mu classical. Then I will get some F tilde mu nu, F tilde mu nu. These are basically the ones which are which are computed in the gauge background. And there is one more piece which I should write, is basically F mu nu classical, delta A mu, delta A mu. So if you expand this action with this, you will get these terms at the quadratic order in delta A mu. So usually, okay, so the field strength that appears in self-duality condition is the field strength with where the covariant derivative is computed with respect to A mu classical.
this is to lowest order,
Yeah, this is, yes. So we are finding perturbation or the fluctuations, the zero modes order by order. So these are basically the linear perturbations around the known solution, which will still give you an instanton solution, and we need to count the number of such fluctuations. That's our goal, because we need to count the number of such zero modes. So we need to count such delta. So it's, I think, easier to also, yeah, by doing this I should have done this in a better way. These two things can actually be written as F mu nu plus minus star of F mu nu, this field thing. So if you satisfy this condition, it's equivalent to that the action, there's no contribution, extra contribution coming to the action. So you can also independently show that when you add such deformations to the gauge field, the action remains invariant. Okay, so let me call delta A mu as some phi mu, just to not write a lot of things. So what are the conditions which phi mu has to obey? One condition phi mu has to obey is that d mu phi mu is 0, and the other condition can be written as basically this. I'll show you how. Sigma mu nu d mu phi mu. So this first condition can be written in this way. How? So this is basically, in order to see that this and this are equivalent, you just multiply this condition by one more sigma. So let's say sigma rho sigma bar mu nu del mu phi mu, and you take the trace of that. So you can write this part as a sum over commutator and an anti-commutator, but the trace of the commutator thing will vanish. Okay, I should have maybe, okay, I didn't write all the computations, but I think from the sigma matrices it will be easy to see, because this commutator is proportional to some delta functions and other sigma mu's, and the trace vanishes because trace of sigma mu nu is 0.
it's commutator, right?
Yeah, the commutator of the trace of multiplication part. So when you take the commutator, this commutator is proportional to some delta times some other sigma.
I think the comment was that the trace of commutator always stays.
Ah, yes, sorry. Two matrices, no, so trace is cyclic. Yeah, so trace is cyclic, so it's always, yeah, it's easier that. Okay, so this is 0, and this anti-commutator is basically, okay, it's in terms of deltas and epsilons, and I have not written the exact expression. What I have written is that this thing becomes trace over, this thing becomes del sigma phi phi rho minus del rho phi sigma minus epsilon mu nu rho sigma del mu phi nu. So this combination basically becomes this using the anti-commutator here. So this is basically the f wedge f condition. You can say, oh sorry, I should have said that for this part I am looking at anti-instanton solutions. So the deformations of the anti-instanton solution. So this will satisfy, this is, here is a plus here. So this will satisfy this thing with a minus sign. And this, you can see that this is just f wedge f, no? Because this epsilon, you can write this term as two terms with a negative sign, and when you take it to the other side, because this is sigma rho, this is rho sigma, so there will be an extra minus sign that will come. So this will just basically say that del mu phi nu, sorry, this will just say I am writing as f mu nu tilde as minus f mu nu. And this is the condition we wanted to set for the deltas. So finding the solution to these two equations is equivalent to finding the solutions to this and this equation. Okay. Now what I will do, I can write these two equations in the following way. So both the equations can be combined to be written as sigma mu, sigma bar maybe, del mu phi nu is equals to 0. One can see how when mu and nu are equal, this becomes sigma square, which is 1. So this gives you del mu del nu, del mu del nu. When mu and nu are not equal, then you can write this as half times the commutator, and the commutator is exactly sigma bar mu nu. So sigma bar mu nu, so you get this equation. So finding a solution to these two equations is equivalent to finding a solution to this. And now this equation I can write it as, I can combine this sigma and d, I can write it as del bar slash on, and this sigma nu phi nu, this is a matrix, no? Because, so let me write it as, so let me call this matrix as capital phi. And basically given a phi which is like delta A1, delta A2, delta A3, delta A4. You can see that this matrix will be, okay, so there will be delta A3, delta A3 from sigma 3 multiplication. Then there is a I delta A1 plus I delta A1 from sigma 2 multiplication. You will get a sigma 1 multiplication delta A1 minus I delta A2, I think delta A1 plus I delta A2. So basically, okay, I should have written it here. Basically this is a matrix. I am just,
What's that? The diagonal ones, do they have a 1 or a 4?
oh sorry, these are 4. Because the fourth element was the identity, so it's 4. So basically this equation becomes del bar on this phi matrix is 0. This is looking now like a Dirac equation type of thing. It's not fully yet because it's acting on a matrix, not on the column vectors. So let me represent, so let me write these things as, this is A, let me call this A, this as minus of A star, this as B star, this is B. So if I write, so my matrix phi is A minus A star, B star, B, and del bar slash acting on phi can be written into two equations. One when del bar slash is acting on A and B, and the other one when del bar is acting on B star and minus A star. Yeah.
Two independent equations, right? And this one seems to be the sum of those two being equal to 0. How is that?
You are saying that this equation is,
Sum of those two being equal to 0.
but actually when mu and mu nu is same, only this piece will contribute. This piece will not contribute because the sigma bar mu nu is 0
This whole thing is a summation, right? Over mu, mu.
over mu and nu. Yes.
This seems to be a weaker condition.
This is one of the equations.
No, yeah, I think what you are asking, it combines the both things, but this is like, in a sense, delta mu nu plus sigma bar mu nu, this part. So you are saying that it's the sum of the two equations.
They are independent matrices.
Yeah.
So
Let's count. This is 4 equations because it's a 2 cross 2 matrix equation.
Yes.
Okay. Now let's count how many equations you had earlier.
Yes. This is 1 and these were 3.
3. The self-dual part
Self-
is 3, and the trace part was 1.
Yes.
So it's just repackaging of those 4 equations into a single.
Yes. Okay, so I'll call this vector AB vector as some lambda, and you can see that this is, I think, I sigma 2 times lambda star. So these two, so now the problem of finding 0 modes of the instanton solution maps to finding the solutions of this equation, del star lambda is 0. And actually, if this is true, this is automatically true, because sigma mu, because you can take the star here. So if you take the star here, you will get a sigma mu star del mu lambda star. The sigma mu star can be written as sigma 2 sigma mu sigma 2, something like this, using the properties of sigma matrices, because these are just identities, imaginary things. So sigma mu star can be written as this. So this is basically del slash acting on lambda star, sigma to lambda star, sigma to lambda star. So if this is satisfied, the equation which is del bar, is it del bar only? Okay, del bar slash on sigma 2 lambda star, this is also satisfied. This implies this. So basically, in the end, we need to just find the solutions of this equation. This looks like a Dirac equation, but it's like Dirac equation for just the upper component or the lower component, because this is a 2-dimensional thing. The Dirac equation, the solution is a 4-dimensional. So if you separate into chirality, this is basically equation for just the upper parts for psi plus. Yeah, it's a Weil equation. Yeah. So basically, now the problem of finding 0 modes have reduced to problems of finding number of solutions of these lambdas, lambda such that they solve this equation. Also, one can note that lambda and I lambda, when you talk about Weil equation, these are just the same solution. You do not consider them as independent solutions, but here they are independent solutions. Why? Because if you compute from lambda what are A and B, and I lambda will be giving IA and IB, you can try to find what are the phi's, and you can try to find what are deltas here. And you will see that the transformations that you will find are different. So I can just write. So let me call phi 1 as the one, phi 1 as the one with which I generate by computing lambda. So phi 1 is basically A, B star, B minus A star. And phi 2 is the solution where I just multiply this solution with I. So IA, IB star, IB minus IA star. Okay. So let's compute what are the delta A3 and all. So del A3, okay. So let me, I don't want to, so from delta A1 computed from the first solution is basically A1, you can add this part so that it's the real part of B. Similarly, you can find what is delta A2. Delta A2 will be like the imaginary part of B. A2, no? Yes. Delta A2 is imaginary part of B. Delta A3 writing this one is saying that it's computed from the first solution. So it's computed is basically real part of A, and delta A4 is imaginary part of A. But if I compute the same deltas from the second solution, you will get another configuration, which is basically delta A1 from solution 2. Now IA is equals to this. So A3 is related to the imaginary part, not to the real part. So I will just copy from my notes. So this becomes imaginary B, delta A2 of second solution becomes real part of B, delta A3 this solution becomes minus imaginary part of A, delta A4 becomes real part of A. So these two solutions, these two zero mode solutions are different zero mode solutions, and they are not even related to each other by just Lorentz transformation. So the number of zero modes is twice the number of zeros of lambda, the lambda equation, the Weil equation. So what we have concluded is that number of zero modes of instantons is equals to 2 times number of zero modes of d bar. D bar slash. Okay. Okay. Now let's try to relate these zero modes to something which is well known. It's called index theorem. So we can try to relate. So if I have a Dirac equation, as we already said, the Dirac equation del mu, let me write it as psi is equals to 0, then psi can be written as psi plus, psi minus. So I can just write the Weil equations. So if I write the Weil equations, I'll get d bar slash on psi plus is 0, and I'll get d slash on psi minus is 0. Because, sorry.
So there will be three such solutions of lambda corresponding to each adjoint.
Three such solution of?
This lambda gives rise to one of the, this delta is one of the adjoint index.
No. There is, sorry, when I am writing this, this is this is a mu a ta. So the adjoint index is already summed over. This mu, there is just a mu index, which is the Lorentz index. This 1 and 2 are not the adjoint index. This for the.
2 are the different lambda and I lambda.
Yeah, yes.
So this is a matrix.
Yes, this is a matrix.
Delta is a matrix.
Yes.
So are A, B.
Yes, so I have not written the TA index. Yes. Okay.
Wait a second, maybe I didn't understand. I thought that.
So what I have written is delta A mu's, no? So he was asking whether it's delta A mu A.
Well, I thought that the reason we had a matrix at all, phi is a matrix because it is an adjoint field, right?
Yes.
So that the matrix structure encodes the
Oh, yes. Sorry, I have said it very badly. Oh, maybe did I do something wrong here? So phi had an index.
Yeah.
No?
Phi was the matrix of delta is small phi, and that those delta A's are themselves 2 by 2 matrices, right?
Yes. I think this is what he's saying. Yeah, it's right. Yeah.
Phi was directly delta A mu, phi by.
Yes. Now delta A mu has a color index also. Each delta A mu. Yes.
So it's actually a 4 cross 4.
Yes. Yeah, what I said was. It's it takes value 1 to 3 actually, and then mu takes value 1 to 4.
That's why the 2 times that thing, because
No. That 2 is not coming due to this. This 2 is coming because lambda and I lambda gives you separate fluctuation configuration, separate delta A mu's. But we are interested in delta mu, which we are not interested in each component. So we are counting the number of delta mu's. Maybe Shiraz is not happy.
I'm sorry, I'm just confused. To start with, if we just go right to the top of the board.
Yes.
This sigma mu, sigma nu.
Yes.
Then del mu, psi nu. There, phi is a 2 cross 2 matrix.
Yes, this small phi is a 2 cross 2
2
matrix.
cross matrix, and that encodes that.
No, not sorry. This small phi is a has an index A, which yes, 2 cross 2 matrix. If
2
you
cross 2
take
matrix with the sigmas.
sigmas, yes.
Right, and that matrix encodes colors.
Yes, so this phi is a 2 cross 2 matrix. Now I have acted this 2 cross 2 matrix and I have contracted the index mu to get a new
2 cross 2 matrix.
But there is still, this delta A still are 2 cross 2 matrices themselves.
Correct. Right. But just let me go through step by step to see what object each is. So that phi there was a 2 cross 2 matrix.
yes.
Okay. Then you decomposed phi as in this form. In that 2 cross 2 matrix structure. Right?
Yeah, I am thinking of phi here as a vector. I am not thinking as a 2 cross 2 matrix. So phi has a new index also.
New index also. Excellent. That's correct.
Yes.
But it was a 2 cross 2 matrix independent of the fact that I had a vector index.
Yes.
Okay. So what remains after you contract the vector is just a 2 cross 2 matrix. Because each phi nu was a 2 cross 2 matrix. Then you multiply that with sigma nu. That remains a 2 cross 2 matrix.
Yes, I agree. Yes.
Okay, so phi there was a 2 cross 2 matrix.
Yes.
Then you opened out, what is that next line? The expansion of phi?
Yeah, so if this is a vector, phi, so if I take this A's as the components of the vector, then if I multiply by sigma, I will get this.
There is no matrix multiplication in sigma and mu.
Yes, this is not a matrix. The alpha beta indices of this matrix are not contracted. No? The new index is contracted.
So it's a 4 cross 4.
4 cross, yes, that's what.
Now
Yeah.
I understand.
Yeah.
I see. So it's 4 cross 4 matrix.
Each
because
component.
The sigma mu, it's like a tensor product here.
Yes. 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 Yes.
Each new you have a tensor product and then you sum overall.
I see.
Yes.
So 4 cross 4 matrix.
Yes.
And so now this here is in which of the 2 matrix spaces? It's in the first matrix.
In the first, yes, in this space.
In the sigma
Is-
mu space. That.
Yeah, this D slash, yes. Now the D,
No, so
which are
that block there. That
Sigma nu space.
in that sigma mu space, right?
yes.
So if you write everything as factor 1 tensor factor 2, this expansion is in factor 1.
Factor 1, yes.
And each of the elements are a matrix in factor 2.
Factor 2, yes.
Okay, yeah. Now please, if you don't mind, just keep going through that whole thing. Just tell
Yes.
us what object everything is.
Okay, so now I am calling these delta A3 plus something A is a, now A itself is a 2 cross 2 matrix, no?
Yeah, everything is a 2.
Yeah, so now if I read off the values of A,
So little a and little b are 2 cross 2 matrices in factor 2.
yes, in basically the color index.
Color space. Yeah.
Yes, in the color space. So that's why in the color space, so this thing is a matrix. When I wrote down the solution, so these are the solutions. So I am reading off the delta A mu's from the solution. And this delta A mu can be written in terms of B and A. This is a 2 cross 2 matrix.
Okay.
Now it's just a 2 cross 2 matrix, which is fine because delta A mu, each component is a 2 cross 2 matrix.
Okay. Sorry, and the phi 1 and phi 2 were what? Those
So
were 2.
these are the two solutions. So basically,
Suppose you had a solution of.
yeah, suppose I had a solution of this equation del slash lambda is equals to 0.
Yeah.
I
so
can
now
just,
let me focus on that equation first.
yes,
In that equation, A and B are 2 cross 2 color things.
yes.
And del slash is an operator that acts on both spaces.
Del slash is also on the mu index is contracted. So it's on the,
So it was
No, but it's also gauge covariant derivative.
no, that is not gauge.
yeah, this capital D. Yes, it's gauge covariant. Yes, there is a A mu TA.
So it's an operator that acts non-trivially on both spaces.
Yes.
Okay, so it acts like a Dirac operator on the first space,
Yes.
but like a gauge covariant
Gauge
derivative
covariant
on
on
the
the
second space. Okay, excellent. So it's somehow acting like on a product of two
Yes.
spaces. Okay. now, fine, good.
So once you know one solution, you can find another solution by just multiplying with I. And I was just writing down the zero modes for both the
You
solutions.
convinced us that those were different solutions.
Yes. And now what I want to see
Okay,
is,
but so the final conclusion was that the number of bosonic zero modes is twice the number of zero modes of that equation.
of the, yes,
Del bar slash of lambda is equal to 0.
yes.
But this object is
But
is
this is same as when if you have a covariant wild derivative.
right.
It's the same.
Adjoint
Yeah.
spinner.
Yes, yes. So
Adjoint-
lambda is an adjoint spinner. Yes, I should have, yes, sorry. I was going to mention it later when I was doing the counting. Lambda is an adjoint spinner. So then,
Now, it's
now,
right.
yes, yes. It's an important point. So lambda is an adjoint. Okay. So, yes. So I wrote down the variations for both the zero modes, and you can see that these two are not connected to each other by any Lorentz transformation. These are two separate solutions. Look here, A3 is, did I write them correctly? I am not sure.
How do I see that in the limit before you wrote down the solution? You would see just like the equation.
Yeah, I think, okay, the thing which is written in like notes which I was following is that the reality conditions on lambda, when you look at it as a solution of a while equation, are different, because lambda, you want lambda and lambda is equal to lambda dagger. You want to impose reality condition, but the reality conditions on phi are different.
Yeah. I mean, A
That's
has
it.
4 different real components. And it's not like, you know, in the while space we're saying lambda and I lambda are the same thing because we can multiply by a complex number.
Yes.
But A itself is real vector. There's no sense in which you can multiply by complex number. So
Yes.
that would be some transformation of A's.
Yes.
So it's a different solution.
Yes.
Other things, if you replace 1 by 2 and 2 by 1, this indices,
Yes.
those are like different solutions.
Yes.
And they are similar.
Yes. Yes.
It's like Z and IZ will have.
Yeah. So here, look, this is A4. This is A3. So these. Yes. Yes.
And by the way, just to say, so this is predicting that one instanton, in the background of one instanton, an adjoint while fermion will have 4 zero modes.
Yes. I have not told the counting yet, no, because I have not told what is K.
I know, but suppose you've already told us that K equals 1 the way it's 0 modes.
Yes. So there are
So
4.
if we halve that, we
Yeah.
get 4.
Yes.
Just want to make contact. In anomaly matching,
Yeah. No, but maybe you can say your comment, and or maybe I'll say
go
that
on.
how it's related to index, and then you can make
Yeah.
the comment. Yeah. So basically, okay. So there is an object called index of an operator. So index can be defined for differential operators on. Usually people do it on on a closed manifold, but you can do it for manifolds with boundary and all. So there is this theorem called Atiyah-Singer index theorem, which tells that the index, which is basically, so how maths people define the index is basically kernel of this operator minus the co-kernel of the operator. And kernel, co-kernel will be basically the 0 modes of D dagger minus 0 modes of D, something like that. And that you can write in physics way as number of positive chirality 0 modes minus number of negative chirality 0 modes. This is an object which is an index, and there is this theorem which is Atiyah-Singer index theorem, which Atiyah-Singer index theorem, which says that this index is a topological quantity. So what I mean by topological quantity is that if I know the background on which it is working, and if I know the manifold, this quantity is fixed. And the nice thing is that with the theorem you can prove that this quantity comes out to be what I think Shiraz was going to say is basically, I want to get the factor of, I think there is a 1 by 32 pi square, F mu nu wedge F mu. So in the gauge background, it comes out to be this, which is exactly the thing which you get in the anomaly. So look, this thing you can relate it to the chiral anomaly. This is telling you the difference between positive and negative chirality 0 modes. which you can write as trace of gamma 5.
So you're saying that that index will be this times a number, right?
Yes, yes,
And that number in this case will be, for k equals 1, will be 4.
yes. So, okay, but this is the difference between plus and minus. But we need to only count the plus things. The lambda was satisfying d bar slash lambda is equals to 0. So we want to count this. We don't want to count the difference. So how can we get the information of just these 0 modes from the index? The thing is that this n minus thing, this in the instanton background, the claim is that there are no 0 modes. So n minus is 0 in the anti-instanton background. I can show you how. So basically, you have d slash of psi minus, you want to satisfy this equation. You want to find the number of solutions of these equations. And my claim is that number of solutions of this equation is 0 in the background, in the anti-instanton background. So what I can do, I can multiply with a d bar slash. So the kernel of d slash is a subset of kernel of this operator. And now this thing I can write is as d square plus sigma mu nu f mu nu. I want to see if it's sigma bar. Yeah, this is sigma bar. And we have seen that sigma bar was self-dual, but I'm working in anti-self-dual instanton background. So this is anti-self-dual. So this term is 0. So I have to say, find the solutions of d square psi minus equal to 0. I have to find how many solutions. But the thing is that if I want to look for normalizable solutions, so index usually only counts normalizable solutions. That do not. So if I want to look at, this is a positive definite operator. So there are no normalizable solutions to this. Because one solution which you can think of is a constant, but constant is not normalizable. So basically the n minus is 0. Hence the problem of finding the 0 modes in instanton background gets related to the index of the d bar slash operator in that background. So the final conclusion is that the index 2 times index of d bar slash, so I should have written this is just d slash is equals to the number of 0 modes. Now notice that this index has a very nice connection with anomaly, because this is nothing but it's a chiral anomaly. So if you, sorry.
So this n plus n minus should be normalizable solution, right?
Yes, yes,
Counting index.
yes.
So they cannot be free particle.
Yeah, EIPX cannot work, yes, yes.
Yeah, but where the Euclidean.
Huh.
So no wave solution thing.
Yes. But yeah, but because I think in mathematics, the only well-defined things are the normalizable things, and you want to just count those solutions. Okay. So, and I think, yeah, now you can make the comment about the anomaly.
Yeah,
that you
just to put many things together. So very, very beautiful. Very beautiful. But, okay. First, you remember that when we were counting the anomalies, we were counting adjoint, if we had an SUN, we counted fundamentals, something that, if we were doing SUN, let's say U1, something transformed with the fundamental of SUN, we counted that as anomaly 1. But it's something transformed.
Yeah, I should write that here. There's a trace over TATB, no? Because there was a trace over these indices. So TAT actually. And this trace is N for adjoint spinor, but is half for fundamental.
For the fundamental.
Yes.
The relative factor here is 2n for adjoint and 1 for,
Yes.
1 for fundamental. This is how we were counting. So now, you see, let's look at that 2n when n is equal to 2. 2n becomes 4.
Yes.
4 is 8 by 2.
So 8 0 modes we already counted in SU2, and there are 4 solutions to lambda.
Right. So the number of 0 modes was that for adjoint, for an adjoint, was that 4. Now, why is the number of zero modes the same as the violation?
Oh,
You see, we're saying that the number of zero modes tells us that we have del mu j mu is equal to f wedge f, normalized so that it's integer. So del mu j mu is equal to number of, is f wedge f normalized so that it's integer, times number of zero modes minus number of anti-zero modes. Why? What is the logical reason for this? Diksha has already given us one reason. If you look at the Fujikawa method of computing the anomaly, this.
Yeah, so so you have to compute trace of gamma 5, no? Because gamma 5 has a +1 eigenvalue for positive chirality mode, so n plus will come with the positive sign, -1 eigenvalue for the negative chirality 0 mode. And this trace is not well defined, so people use Fujikawa method to compute it. So you add a minus beta d slash square, d square maybe, to this to count the trace. This is the computation of chiral anomaly, if you see. So because this is basically when you want to seek a chiral anomaly is exponential I gamma 5 acting on size, no? So this is basically tells you how the path integral is changing the, yeah, so this is a, yes.
Excellent. So one reason is this technical reason, that this is what appears in the Fujikawa. But there's also a logical reason. And the logical reason goes as follows. Suppose I'm doing a calculation in an instanton. Claim is that a certain charge is violated by some number of units. Right? That's the claim of the statement del mu j mu is equal to number times f by f. If that number was 4, it would be violated by 4 units. All correlation functions would be 0 unless charge conservation was violated. In this background, unless charge conservation was violated by 4 units. Now, how could that come about? How could it come about that I'm doing some path integral, some nice path integral, some nice background, and charge is violated and that too by specific amount? How could it come? Well, the way it comes about, as Diksha I think would say at some point, but anyway, the way it comes about is that there are fermionic zero modes in this background. Now we're doing a path integral over fermions. And you know that the integral of a fermion of 1 is 0. So if we take the fermionic field and we expand it in all modes, then effectively we're doing the integral over the coefficient of each of these modes. Do you know what I mean? That one way of defining a path integral over a field is work in a basis, eigenbasis of some operator, and do the path integral over the fields is the path integral of the coefficients in the expansion of the spaces.
Yes.
So let's take that definition. Okay? So now we've got coefficients of all the non-zero modes and coefficients of 0. Coefficients of non-zero modes are fine. They give you something non-zero because those non-zero modes appear in the action. But the coefficient of the 0 modes will just give you 0. Because the 0 mode just does not appear in the action. The only way to get something non-zero is to put insertions.
Yes.
And you need as many insertions as 0 modes
Yes.
to get something non-zero. And therefore the only correlation functions that will be non-zero are those that violate charge
By the same amount.
by the number of 0 modes, because you have to put those insertions without, or you get 0.
So we can say that the measure includes the 0 mode, so measure changes by that.
If you want. Okay. So this is the logical link between number of 0 modes and charge conservation. Because there's 0 modes of fermions. So you get 0 in the path integral unless you put insertions to saturate. And you have to put exactly as many insertions as in order to get.
Yes.
Okay. Those of you who are in my field, in my string theory course will remember very similar logic for BC 0 modes.
I have to say that it's the same logic as for BC.
Yes.
Yes.
Correlation functions number of zeros.
Exactly. And for the same reason.
Yeah.
There was an anomaly.
Yeah.
There again, d mu j mu of host current was not 0, but some number times r. Okay, so it's the same kind of thing.
Yes.
Okay.
Okay, so this is, and also notice that this is nothing but the instanton number, no? F wedge f was the instanton number because this was a boundary term and which gave us an integer. So this is k. So for every adjoint you will get, there was a factor of 2 somehow. There is a factor of 2 here. Sorry, So for every adjoint fermion, you will get 2 kn number of zero modes, where k is the instanton number because this number is k, this gives n and there is a 2. For every fundamental one, you will get a k. Okay.
Right? And that was exactly the country we did in anomaly, right?
Yes.
It was fundamental contributes 1 times f by f. F by f was k.
K. Yes.
Adjoint contributes 2n times
Times
f by
k.
f by f is k.
Yes. And now the number of bosonic zero modes in the sense the number of mu zero modes is twice this. And remember lambda was an adjoint fermion. So those number of zero modes delta mu are basically 4 kn because you multiply 2. So we can see for n is equals to 1 SU2 this is 8. Those are exactly the 8 parameters, 8 Goldstone modes we saw in the solution. So this is the counting.
And this ensures that the number will be 16 for 2 instantons.
Yes. Okay. Now the next thing that we will need, next thing we will need is, because as Shiraz was saying, we will need to, so what we have to find? We have to integrate, we have to integrate over the instanton action. So we have to do a path integral in presence of instanton action. So we have to integrate over zero modes. But when we have to integrate over zero modes, we need to know the metric on the space of zero modes because there is a determinant that will appear. So the space of zero modes is called a moduli space. The moduli space name is common. We always say, so whenever there is a configuration that doesn't change the action, is the moduli space, the numbers. So now we need to know the metric on the moduli space because when we will do the path integral, that determinant will come.
And maybe just as a preliminary to what you're saying, you see, these instantons have these zero modes, one of which was position. Now, what the intuition behind the fact that there are twice as many zero modes for 2 instantons is this. It's fake intuition, but let's first say it. We can take one instanton here and the other instanton very, very far away. If they're very, very far away because the fields die out, they don't interfere with each other. And so then this instanton is doing its own thing and this instanton is doing it. Okay? But of course this was far from a proof of anything. Because it could have been that the interactions would scale like 1 over r to some power violated the solution at that order. Could have been that some of these modes are lifted. This is guaranteed that doesn't happen. So these solutions that are very far away, you can multi-particle them and correct them to still make a solution. Now when they come nearer, it might be hard to look at them and see that they are 2 instantons. When they're very far away, they can obviously one solution of this and one solution of this. When they come nearer, they're all mixed up. So this whole thing is guaranteed that there will be those many solutions. Always a 16 parameter solution of 16 parameters into this solution. Though they may look very weird once they come together. Sorry.
Yeah.
And the formula that you wrote for index is a theorem. You have not shown.
Yes, it's a theorem. Actually, you can. There's a very nice method to derive it using Witten index. So there is a 1-to-1 map between the gamma 5 operator and -1 to the power f, d slash square and the Hamiltonian of the quantum mechanics. So you can compute Witten index with the target space where this d slash operator is acting. And that computation gives you this. And yeah.
And even logically, it follows, right? Because this thing should both be the anomaly. See, we know that from one loop calculation this is the anomaly.
Yes.
But as we've seen, the anomaly is an anomaly by the charge conservation because of the number of zero modes in the instanton.
So there is a very nice connection between anomaly, instantons, index theorem, Witten index. So all this fit together and you will always see this factor coming everywhere.
And just to say, of course, this is not rigorous, but the logic makes it clear that the number of zero modes, that the number of zero modes should be related to the instanton. Okay? So these guys make it very precise, and as you said, in many different ways you can see. But as a physicist, just this fact that charge conservation is violated by zero modes
Okay. So,
Sorry, I just to say one more
Yeah,
thing.
yeah,
That's
sure.
because charge conservation is d mu j mu is number times instanton.
yes.
So charge is violated by instanton. So the number of zero modes should be determined only by the instanton. And by this precise relation.
Yes.
So it seems very reasonable from this point of view. Now, no mathematician would regard what I said as a proof. But that's why we're not mathematicians.
I think the Witten index proof, even mathematicians, is the full rigorous.
So
Yeah.
what you said followed once we know that del mu j mu is instant.
But that we know from a one-loop calculation point of view. You read Weinberg, chapter 20, he'll show you this, right?
Yeah. The triangle
Just
diagram.
one loop. This is something all of us could do, even I could do on the board. You know, on a good day. Yeah. So, so that from our own methods we know it. We don't have to rely on some other. From our own point of view, we know this is true. And then it's very reassuring to hear the mathematicians say they agree. Okay.
Actually, if you try to read the maths paper which proves the theorem, it's very hard to decode. And then there is this paper by Witten and I think Witten Alvarez Gomez, which is like 4-page paper, and the proof is like very simple. So, yeah. Okay. So, yeah, so as I said, we will need the metric on the moduli space, because when we'll integrate, we'll need a measure, the determinant. So, okay, let me tell you what is the metric on moduli space. So let's say I was denoting my my zero modes as phi mu, no? Phi mu. And let's,
At some point, you feel free to use the other side of the board. So
yeah.
when you want to, so that people can see people who,
Okay.
if you want.
Yeah, maybe.
Whenever you want.
Yeah. I don't know, it's already 12:50. I don't know how much detail I should.
Go to 1:30.
Yeah, because I want to, so the things I want to cover is this metric, which will give us some factor of rho and v, which we will need in the computation of the mass. And then I'll go to this computation of the mass directly. So, okay, so what do I mean by the metric is basically, let me call, I'm using the same notations again and again, I'm sorry. So, I labels the fluctuation corresponding to that particular zero mode. So, I labels the zero mode. So, for example, if I are corresponding to the translation, I will write as del A by del of the x naught, and then you know that you can add a gauge thing. So, this is the notation. So, if I write, so I will write usually here as, for the translations, I will write this as mu. This is how I will write my fluctuations. For example, for the scaling rho, I will write it as del A rho A mu by del rho. This is the fluctuation, no? This is the delta thing. And you can always add a pure gauge thing. Lambda, I will call it lambda rho. Why you add this? Because you want this final phi to be orthogonal to this. So there is this freedom of adding this lambda. So this is how I will label my zero modes. And now I have to look at the metric on this space. So if you just forget about this index, metric is in between these indices, mu indices. So there is another. So this new index can go from 1 to 4. These are the 4 translation modes. Rho is just rho, it's a one index. It doesn't take any other value. And the next one is A, which are related to the 3 gauge things. So del A mu by del theta A. Theta A is the small gauge transformation. Del mu lambda A. So A goes from 1 to 3.
So you're going to tell us about the metric on one instanton.
Yes, one instanton model. So I am always SU2 k is equals to 1. So there are these 8 moduli. So the metric is the 8 cross 8 metric on this space. So when I say G mu nu, I am never referring to these indices. I am always referring to the ones in the bracket. So these are telling me that I have to take, I have 2 zero modes. One is the zero mode with respect to x mu, one is the zero mode with respect to x nu, and you want to see how the dot product works, what's the metric. So it's a 8 cross 8 metric. So we can just, anyway, I can use the other code. So we can just write the metric, I'll just show the metric on this mu nu thing. So one can actually show that G nu rho of the off diagonal things, G a rho, G a nu, these are 0. The off diagonal things are 0. Only the diagonal things will contribute. The metric is diagonal.
What is the definition of the metric?
So the metric on the moduli space is like when you move in the moduli space, what is the distance? It's basically distance between two. It tells you about the distance between two zero modes. In
How do you find it? What physics calculation can you do? I can imagine that you get the volume form of the metric.
Yes.
So you need to integrate over the space of instantons with a measure.
Yes.
So the volume form is that measure.
Yes.
But how do you get the actual metric?
So metric usually the definition basically, if I want G mu, G I J let's say, is integral d for x trace over phi. So you trace over both mu index and the color index. There's just the I index which labels the derivative with respect to what thing you have taken the derivative, ij. So there's a mu mu, and this trace is telling you the trace over the color index. So you compute this thing.
I see. Thank you.
Yeah.
So you're saying we have a metric in field space.
Yes, yes.
In UV field space.
In field space, yeah. So that's why it's telling you the distance between two different fluctuation solutions, in a sense.
And that metric in UV field space was basically what you wrote, and that's the metric over whose measure you use, whose volume you use to define the path.
Yes, when we integrate all the zero modes.
So it's a natural metric in field space, that induces a natural metric on.
Yes. I'm sorry, the notation is a bit confusing, but yeah.
It's very clear.
Can I ask you?
Yes.
So, what indices are there on G?
G is ij. So these are basically the indices with respect to which we have taken the variation. These ij can be the translation indices or the rho index or the A index.
But I'm sorry, Diksha, in any physics calculation, will we ever encounter the metric itself or only its determinant?
I think just the determinants, because you integrate over the zero modes and in action they don't appear. So there's no other place where they can
So
appear.
really what we care about is the volume.
Is the volume form. Yeah. I just wanted to compute one component of this metric and then I'll just write the volume form. Because, so one component, meaning we can try to compute when ij are both related to translations. But translation with respect to different thing. Mu, one is with respect to x mu, one is with respect to x nu.
Yeah, I just wanted to differentiate this with, let's say, solitons, where the metric on moduli space is very meaningful because it's the kinetic term
Yes.
for the various zeros. So that metric itself is very physical.
Sorry, what do you mean by kinetic term for zero? Zero modes don't have a kinetic term.
They don't have a kinetic term if they're zero, but now you make them functions of time.
Okay, for the, yes.
Okay, then these become AI dot
Yes,
AJ
yes.
dot GIJ.
Yes.
So that low energy effective action has a metric. So that whole metric is very meaningful. Yes, more the volume of
It was, yes. And we'll need the volume. Why I'm doing this computation? Because we will try to match the powers of scalar expectation value and all with the ADS potential and with the one we compute from instanton. So we need those determinants. This will give you some powers. So, okay. So let me, so what is, so I want to compute the product between, so let me write mu, this is the gauge index, and this nu is the transition. So this is basically del A mu by del x naught nu. And I have a freedom to add the gauge thing, but I'll add it a bit later. So what is this? This is just minus of del A mu by del x nu. Why? Because I don't know where I have written the solution. Because remember, the solution appears at x minus x naught mu, no? So if you take the derivative with respect to x naught, it will be minus of the derivative with respect to x. So this is with respect to x, this is with respect to x naught. So here we have to take with respect to the zero mode, which was the x naught. So this thing, And okay, and now you can add the gauge thing. So basically, the gauge, the lambda I, which is lambda nu for this case, you can choose is a nu classical, a classical. So therefore, the gauge thing that you had to add, so there was a plus d mu lambda I is, okay, there is a plus d mu lambda I is plus d mu a nu. So this is a nu, the classical, the instanton solution gauge. So d mu a nu, which is nothing, just f mu nu classical. This is f mu nu classical. You can ask why we choose this gauge. This you have to choose such that the solution is not a trivial solution. So you have to choose it in a particular way. I don't have any physics intuition of choosing. The nice thing is that when you compute this metric, this will just now become the classical action, because you have to f mu nu, and you have to take trace over this. So this component is just S classical. So G mu nu, which is with respect to the translation, is just S classical delta mu nu. And similarly, you can find G rho rho, which is both are with respect to the scaling. This basically gives you 2 times S classical, and G A, which is with respect to the gauge. I'm sorry, I'm not writing this computation because this gives you half delta AB time rho square times S classical. Actually, this rho square is important because this will come in the determinant. So and all the cross things are 0. Is it okay? Maybe yeah. All the cross things are 0. So the determinant, so this is a 8 cross 8 metric, which is basically there is a S classical delta mu nu, which is 4 cross 4. Then there is a 2 S classical, and then there is a 3 cross 3 metric, which is half delta AB rho square S classical.
The rho square we can get some rough intuition from. As far as. If we think of this as the broken part of the rotational sum, that's broken because we've got a vector. The length of that vector is roughly rho. Okay? And therefore, what we're getting is the metric on a sphere of radius rho.
Yes.
And therefore, that will be
There is a rho square. So the determinant of this metric, determinant of this G, let me call it say, is basically there is S power 8 will come. So I'll just write, let's say, square root of determinant, which is the volume form. So it will be S power 4, S classical power 4, and then there is rho power 3, because there are 3 terms with rho square, so rho 6, so the square root is rho 3. I think that's what we need. I'm not writing the 2 factors and all. So this, when I put S classical, we remember was this, 8 pi square G square over K, this. So S classical is this, so this you can write it as basically some rho cube. I'm again not writing the 8 pi factors over G8. So actually this rho cube factor is important, which we'll need. Other things are fine. Yes.
How did you write that formula
For G mu nu, so G mu nu is basically trace of phi mu phi nu. Phi becomes F mu nu.
He wants to know what is the logic for that first one?
The first, this one, no, phi.
The top.
G mu nu. If you want to compute I think of it as a distance measure on phi, the distance between 2 phis. Phis are the fluctuations. So distance between 2 phis is basically phi square, and then you trace over every other index which is possible.
But I think Siddharth is asking, this looks natural, but was it forced on you somehow?
Yeah.
And let me give you my response. You know, all that we do is, we're doing a path integral. We need to know the measure of the path integral. So the path integral, we need a volume. Now it's sometimes convenient to think of that volume form as volume form arising from a metric on the space of fields. Okay? You don't need one, but it's sometimes convenient to give more information than that volume form, namely the metric on the space of fields. Once you specify the metric on the space of field, you define your path integral measure. So the path integral measure that we usually use is the volume form that emerges from there. From that metric. Now you could have chosen another metric. One that would give you the same volume form. That will give you another metric here.
Yes.
But finally, what she's actually going to use is the
Volume form.
The
Yes.
volume form will be the same. So this is a convenient, as far as I see it, maybe there's more, but as far as I see it, this is a convenient choice that we know will give you the correct answer because it correctly reproduces the path integral. Okay? This is often a good way to think. For instance, when we do quantum gravity and we have to specify the metric on the space of all
Metrics.
metrics, it's useful to give a metric on the space of metrics instead of a volume form on the space of metrics. Because it's very easy to write on an actual diffeomorphism invariant metric on the space of metrics that will ensure that we've got a natural diffeomorphism invariant volume form on the space. This is a very standard thing.
You're saying this is not a unique metric.
It's not unique because once I can give you many different metrics with the same volume form. I change one component of the metric here and the
Yeah, I
other
can
one
change
of
this.
it.
I can add a 1 by rho square here, and there's no,
Right.
like I can do some things. But yeah, I have to add corresponding.
Right. And in doing a path integral, all we ever care about is the volume form over which we're doing the integral. So it's not unique, but it's certainly extremely natural.
Yes.
And it will give you the right answer, so why not use it?
Yes.
Okay, there may be more to say about this, but at least this is true.
But also you are not using it more than the volume.
We're not
Volume.
using it more
Yes.
in the volume form, but it's often easier to compute the metric.
Yes.
See how Diksha computed the volume form.
Yes.
She first computed the metric, which was an easy calculation, and then computed the volume form.
Right.
Had you only had the
What is the
volume,
other way you can check that this volume form is the correct one?
is there another way? You could. I mean, you could just start with the volume form on the space of
I'm
fields.
sorry, you said that volume form is known to be like, it will be the volume form, but the metric can change.
He's saying, what's the other way to compute a volume form?
You can say how independently check that this
You want to know what is the right choice for volume form?
yes. How?
It's the derivation of path integrals from canonical quantization. When you derive path integrals from canonical quantization, you get path integrals of the given measure.
Yes.
Okay? Now that measure follows from this volume form. Because basically what you do is discretize the field. And it's a flat metric of these discrete parameters. And that's the metric you run. Okay? So if you do Feynman's derivation, you will land on this. You will land on the volume form that follows from this metric.
Actually, metrics on field space are very useful. Like in non-linear sigma models, I think we will do some sigma models. The coefficient in front of the kinetic term. So whenever there is a quadratic term, the coefficient on front of that, because ds square is gij times something quadratic, no? So
Yeah.
the coefficient in front of the quadratic term you usually
Yeah.
Is
But
it?
just to distinguish that example, there the metric
is
itself
useful.
physical.
Yes,
Because gij enters the low energy effective action.
yes,
Here,
It
only,
is.
as far as I can see,
yes,
only
yes,
the volume form.
yes.
Because there's no time.
Time. Okay. Okay, so this is what I wanted to say. This is all what I wanted to say about instantons. Now let's go to the calculation of the superpotential, Fleck-Dine Seiberg superpotential. So, okay, let me. So I will write the. I'm using ADS word. So I'm looking for a K. So if there are NF flavors, and you are in SU in theory, in n is equals to 1 supersymmetry. And for NF less than n, Fleck-Dine and Seiberg gave that the superpotential is basically lambda power 3 n minus NF over n minus NF, det of m, which is basically m was q bar, q and q bar are the fundamental and anti-fundamental chiral superfields, minus 1 over n minus NF. Now, there are few reasons why we believe that for nf is equal to n minus 1, this should come from instantons. So one of the reasons is the following. As I think Shiraz already said, that the anomaly, so there is a, you remember there was a U1R symmetry which was anomalous, and then we defined R tilde. So the anomaly in U1R is basically 2 times n minus nf times the instanton thing, the f wedge f star f. This is the instant number. So every instanton, any instanton configuration will come with a come with this charge. So this will be the charge, and for superpotential the R charge has to be 2. So when nf is n minus 1, the charge from instantons matches the charge for W. So it's conceivable that instanton things will contribute to the superpotential. So only for nf equal to n minus 1, not for other nfs, because this becomes 2. So this is same as what we want the superpotential, what charge we want the superpotential to have. So instanton generated terms will have this charge. The other reason why, so this was like I think reason 1. The second reason why we expect the instanton things is by naive counting of powers. So I don't know if you remember that if you use this superpotential and you expand the action, the fermion term appears with as this del phi I, del phi j, psi j. So if we do the superspace integral and then you expand, the fermion terms appear as this. So the fermion mass is related to the second derivative of the superpotential with respect to the scalars in the field. Okay, so I should have said this earlier. So let's say we are working in a vacuum when the scalars, the scalars of Q, I'll call them phi Q and phi Q bar, they gain some expectation value. So they have an expectation value V, or I'll consider this to be diagonal. So actually it's delta Ij. This V and the I goes from 1 to nf. And the same expectation value, this is the expectation value of the scalar field, the same expectation value for the phi Q bar. This is what we were doing before. No, we gave the expectation value to the fields. So notice that in n in n equal to n minus 1, there are n minus 1 of these V's. Hence, the gauge group in this vacuum is completely broken. So before you had SUN symmetry, now n minus 1 part of them is broken, which means that it is completely broken. Okay, so now what I will try to do is I will compute the mass m using this formula for nf equal to n minus 1, and then we will try to reproduce the same mass coming from the instanton generated potential. That's the check you usually do. So the mass of the fermion, so if I take the derivative, so this I replace it as v power 2 nf, I can replace. So there is a lambda, I can use nf equal to already n minus 1 maybe. Okay, I can use nf to be n minus 1 already. So this is 2n minus 1 plus 1. 2n plus 1, v power 2 nf was the determinant. Then there is a 1 nf minus n minus nf. This thing is 1. So for nf equal to n minus 1, this is just lambda 2n plus 1. Is this fine? This 2n plus 1 is correct, no? Nf is n minus 1, yes. And this v becomes minus 2 nf. Now we want to compute, so this is the superpotential W. Now we want to compute the mass. You have to take two derivatives with respect to phi, which we can take like with respect to.
Chosen a very symmetrical vacuum.
Yes. All the, yes. So we can take two derivatives with respect to v, that will give us the mass. We just need the power. So the mass will be proportional to lambda 2n plus 1, v power minus 2nf minus 2, no? So when I take two derivatives, this is just v power 2 nf. This is just v power minus 2 n. We will try to reproduce these exact powers from the instanton computation. Okay. Okay. Also, as I think Shiraz said in one of the earlier lectures, since in this case when nf is n minus 1, the gauge group is completely broken, instanton calculations are reliable because when the expectation value is large, you can think that the gauge coupling is very small. So all the calculations that you are doing are reliable. Okay. So we will try to reproduce this mass. So mass will proportion. So I'll actually work with SU2. So n is 2. So it will be lambda power 2n plus 1. Sorry, lambda power 5, v power minus 4. I'll try to reproduce this power from instanton computation.
So instanton calculations are reliable when V is large.
Yes, but there's a counterintuitive thing which, okay, I'll say one thing. Yes, that is true, what you are saying. So this is for n is equals to 2, SU2. Okay, so let's write the action. What is the bosonic part of the action? And we can try to, so we want to compute the instanton configuration. So the bosonic part of the action, the Lagrangian will have a d for x, write a 1 by g square, f mu, there is a trace, I am not writing the trace, f mu plus d phi, this is the, let me write as phi q plus d phi q bar. This is the bosonic part of the action for n is equals to 1 supersymmetric case with one flavor. It's SU2 with one flavor. So there is 1 phi, 1 q and 1 q bar. So there is a 1 phi q. Now the solution, the instanton solutions that we were previously working in, they were just the solutions of this action. The point is when there is the full action, when there is a source. So if I compute the equation of motion, what are the equation of motion? Equation of motion is del mu f mu nu is equals to j mu. This is the equation of motion. So when the j nu is 0, there is no instanton solution. The one way to see this is basically if I scale this. No, sorry, there is some question. No, so one way to see why there is no instanton solution is basically scale this action. This is conformal, so there is no lambda that will. There is a lambda minus 2 that will appear here because there is a you scale a mu goes to lambda a mu. So there is a quadratic piece in A. So this term will scale as, okay, I don't know that. So basically what will happen is that the action is minimized when the instanton size goes to 0. I wanted to make that argument by scaling, but I am now getting confused. So the claim is that in presence of sources, there is no instanton solution. And one can see that fact is by some scaling argument. Now I am getting confused because I am getting an opposite power, minus 2.
How are you getting minus 2? Say
so what I was trying to do was basically this. Let's scale a mu of x goes as lambda times a mu of lambda x.
Right.
Now this term is invariant.
Is it lambda times lambda? You're making.
Yeah, I think this will make rho to be lambda inverse, maybe. That's the thing I am confused.
A is like 1 by 8.
Yeah, you probably. Yeah, please go. Yeah.
You are saying a mu is 1 by x, so maybe it's lambda inverse. Yeah.
If you have dimension, you are doing dimensional thing.
Maybe.
No, it's right.
Because there is a lambda here inside, so there is a 1 by lambda here that will come here.
Yeah.
Yes. And now you basically, you see this term is invariant, but this term has a a mu square phi square piece. The other pieces have derivatives,
Yes.
but there is a mu square phi square piece, so which goes as lambda square.
Yes.
So these terms will pick up a lambda factor.
But there's also
Minus
the
2, I think.
d4x.
Huh?
There's also the d4x.
Yeah, so that's minus 2, that's why I think
That's right. I see.
minus 2.
Yes, good.
Now I think, okay, the argument which I'm unable to fully understand was that when you scale x as this, the size rho scales inversely, and the action will be minimized when, here you can see action is minimized when lambda
It's infinite.
infinite, so this means rho is 0.
Yeah.
So the size of the instanton becomes 0.
And you see that row scaling just by putting it into the solution.
Yes, yes. Yeah, I remember now that you put this into solution, you want x square rho square factor to come out, so the lambda, when you take lambda out, there's a lambda inverse which will come here.
Yeah.
Yeah.
So,
Oh, okay. I was forgetting. Yeah, okay. So basically, the point is in presence of sources, the action is minimized when instanton size goes to 0.
okay. And let me just make one comment here. You see the whole action here, if you think of phi also as a field, continues to be at least classically conformally. Because phi also is a dimension 1 field. D mu phi is dimension 4. That's okay. What the argument Diksha is making is the following. We know that there is a vacuum. We're looking for a vacuum where phi takes a constant expectation.
Yes.
That constant expectation value breaks this conformity. The source is going to be generated from that constant expectation.
Yes.
So we'll have two powers of that constant times whatever else. So this is spontaneous breaking of that scale invariance. And in such a vacuum, Diksha's just argued that all instantons want to go to 0 size.
1 to 0 size. But then you can say that, okay, when the expectation value of the scalar was 0, there was an instanton solution. When it becomes non-zero, there is no instanton solution. So it's, but what we can do is we can do things in perturbation theory. We can do things such that the expectation value of scalar times the size of the instanton. This is very small, less than this g. And in the perturbation, we can, so we'll take the first solution, which is v 0 to 0 solution. Then we can add the term order by order in v. Actually, there's a better method to do this, which is you have to add it's called constraint instantons. And I also don't understand this very nice, but also time is running, so I'll maybe skip that part. So I'll just say that if you do order by order, so at leading order in this row V, basically what you get is d mu phi f min, you want to find solution to d mu f min is 0, and the scalar equation is del square phi 0. And there are solutions. This solution is exactly what we had written, this one, because I am in SU2 again. So this is this solution, and the phi solution actually can be written as V times sigma mu x minus x naught mu over, so sigma bar x square plus rho square power half. And if I take this configuration, I compute the action. So this contribution you already know, this was 8 pi square over g square. There's this extra piece, when you put this, V is the expectation value of scalar in the vacuum. When you put this here, so what you will get, that action is basically 1 by g square, 8 pi square plus 4 pi square rho square v square.
Okay. And let me just say one thing about the equation. You see, this background expectation value makes there actually no solutions. What that means is that, roughly speaking, you can think of it as if you plot the action of the instanton versus rho, instead of being flat, it curves down with its minimum at rho equals 0. Okay, so all instantons want to be driven to 0. But you see, let's look near 0 size. Near 0 size, this potential is very, very flat. Why is it very, very flat? It's because near 0 size, the background instanton has huge field strengths. Because f wedge f is always a constant, and it's concentrated in some very small size. So the F's are very large. Now the background V is some V. So it's a small perturbation on this huge background field still. Okay? And therefore, this V can be sort of ignored when the instanton is very small. On the other hand, when the instanton is very large, the background F is very small, V is now big.
Yes.
So it cannot be ignored. Okay? Another way of saying it is dimensional analysis. Clearly, the extent to which the solution is not a solution is proportional to V square.
Yes. So basically what he's saying that this J is proportional to V square.
Right? Because the right hand side of the let's say del mu F mu equation
Yes.
comes from
The current
the coupling of gauge field to the scalar field,
is phi del mu phi.
and that is quadratic in
Phi.
phi. Okay? So clearly it's proportional to V square, but you know, if you want the relative contribution of a term to something else, it's going to be dimensionless. V has dimension 1. So it has to be proportional to something of length dimension 1.
Yeah.
There's only one thing in the background, which is rho.
Yeah, one can also see that the first order term was proportional to 1 over rho square. The next order term we are saying is proportional to V square. So if I take this rho square out, the perturbation parameter is rho square V square.
Exactly.
This is the delta F, I'll say F2, the second order, the next order term.
Right? So one were trying to, as Diksha says, one were to try to solve the equations order by order in V. It will be order by order in rho times V. Just dimension. It has to be dimension in this number rather than that. So that's another way of saying it. So even though there are no real solutions, there are almost solutions. And the almost solutions are as good for physics purposes as true solutions.
Yes. Okay, one part which was a bit confusing to me was that we trust instanton calculation when expectation value of V is large, but these solutions exist when V is small.
But you always have, you take V large compared to lambda QCD,
But yeah,
rho small compared to V.
yes.
Do both.
Yeah. Okay, so these are the bosonic zero modes. So bosonic zero modes are basically, so these are the bosonic solutions. So these are the A mu solution and this is the phi solution. Now we need to know the fermionic ones. So now let's count the fermionic zero modes. How many zero modes are there? So in this theory, it's a n is equals to 1 theory. There's one gaugino which is in adjoint. So adjoint, so the fermionic zero modes, if I want to see. So adjoint field contributed to 2 kn, no? K was 1 and n is 2. So there's 4 zero modes due to gauginos, and then there are 2 fundamental fermions. One is fundamental, one is anti-fundamental. So there are 2 fermions. Each of them contribute mod k, which is 2 times. You will get 2 times mod k. K is 1. So there are when you can ignore these things, when you can ignore the right hand side of these equations, there are 6 fermionic zero modes. But when you turn on the expectation value, some zero modes will be lifted. Now, you remember we understood the bosonic zero modes at Goldstone modes due to breaking of some symmetries. Some of the fermionic zero modes can also be understood as breaking of symmetries. 2 of these zero modes are very important. I am calling this lambda SS. So these two, the 2 zero modes, okay. These are the Goldsteinos corresponding to breaking of supersymmetry. Because I have to tell you that this instanton solution breaks some supersymmetry. So remember, I don't know if you remember that the variation of so there are 2 supercharges, Q and Q bar. Sorry, I am calling these are the supercharges. Okay? Because it's a n equal to 1 theory. N equal to 1 theory in 4 dimension has 4 real Majorana, 4 real component spinors. So there are 2 Qs, 2 Q bars. So delta of Q is equal to F mu nu sigma mu nu. Let me write correctly whether it's sigma mu nu or sigma mu nu bar. F mu nu, sigma bar nu, epsilon. This is the gauging. So there is an alpha index here, there is these metrics multiply and there is a alpha index that will come after it. and the variation of the variation of Gagino under the bar, Q bar, is basically F mu nu, sigma bar mu, sigma nu, epsilon bar. Now notice that if we are looking in a self-dual solution, which of them is 0, sigma. So if we are looking in the self-dual solution, this F is self-dual, but this is anti-self-dual. So this delta Q bar on lambda is 0, but delta Q on lambda is non-zero. So this instanton solution, this F mu nu background, breaks half of the supersymmetry. It preserves the Q bar supersymmetry, but it breaks the Q supersymmetry. So this is a generic feature actually, that instantons preserving some supersymmetry is a very important feature. That's why they are BPS solutions also, because they are the solutions which are vacuum solutions, but they break some supersymmetry, preserve some supersymmetry. So this particular instanton solution, which is the self-dual one, breaks half of the supersymmetry. Hence, there were 4 supercharges, 2 of them are broken. So there needs to be 2 Goldstone modes corresponding to broken supersymmetry. These are called Goldstinos, and these lambdas, which I was, so 2 out of these 4 zero modes are basically the Goldstino corresponding to broken supersymmetry. And actually, when we include the expectation value of V, only these 2 will remain zero modes, other 4 will get lifted. So the actual zero modes, you can always think of them as Goldstone modes coming from some symmetry breaking. Okay.
I'm sorry, just probably a stupid question. If we look classically, the theory preserves superconformal.
Superconform. So yeah, so there are other 2. So there is a, remember when we had superconformal, there were Q's and there were S. S alpha and Q alpha. S alpha was somehow basically X slash on Q, something like this, approximately. So actually, since Q bar is broken, since Q is broken, the S corresponds. So there are, let's say, S and S bar. So S corresponding to it will be also broken. So there are 2 S which will be broken. So actually, all 4 of these Goldstino can be thought of as the Goldstinos corresponding to the broken symmetries. 2 corresponding to breaking of supersymmetry and 2 corresponding to breaking of the superconformal charge S.
And therefore there will be 4 exact zero modes?
No, actually there are only 2 exact zero modes. This statement was worrying me. I read it at 2-3 places.
Linear combinations of exact.
Yes, there are some linear combination. In the end, there are exactly 2 zero modes when you turn on the expectation value of P.
Yeah, this is sort of a little like, when you have a brain, you break both translation invariants as well as rotation invariants. But the number of Goldstone modes are just those coming from the translations. You can ask, what do the Goldstone modes due to rotations? And if you work it out, those are sort of linear combinations of these.
Yeah.
It's a sort of confusing thing, it's true.
Yeah. Okay. So now we know the number of zero modes, and we know, okay, we need to know how the other zero modes are lifted. One of the things we need to know. These are lifted because of the presence of Yukawa coupling. Initially in the absence of the expectation value of scalar, the equation of motion for the fermions were like either d slash or d bar slash on size was 0. But now when you turn on the expectation value, there is a Yukawa coupling term which couples the Gagino with the fermions in one of the fundamental anti-fundamental. So the Yukawa coupling term usually looks like this. Sorry. Yeah, so let me write the fermions as a column, all the fermions as a column vector. So I'll define this psi, which contains Gagino, which has a index, the color index also, which contains psi of the okay, these Q are my chiral superfields. So these Q, now I'm not talking about supersymmetry. So any Qs which will appear are the chiral superfields, and psi Q bars of the anti-fundamental superfield, fundamental and the fundamental. So initially, without turning on the expectation value, the kinetic term, the term in the action was basically psi dagger some matrix M psi, where this matrix M was basically diagonal. They were D slash, D bar slash, D slash, something like this. So the kinetic term of the fermions was just the free kinetic term, which is there. But when I turn on the expectation values of scalars, remember there is this term in the action. There is a term which is G times lambda A Ta phi of the scalar field of the qth Q quark and the fermion of that same quark, the same chiral superfield. So there is this term. So there is the off diagonal piece which gets generated to this matrix, which is an off diagonal in lambda and psi. So this matrix now in the presence of this expectation value changes, and that's why some of the fermion zero modes get lifted, because now they do not satisfy the equation del slash lambda is 0. There is a del slash lambda is equal to some. So okay, in the end what we will, so actually one can compute, so what we need to compute in the end. I want to say what, so okay, delta M will have these components here. So there will be G phi, I am replacing it by V. Then there is a Ta due to lambda. There is a square root of 2 somehow. So there are some components here, here. So these are the things that will appear. Okay. So this is the same as this G. So now the equation of motion in presence of expectation value becomes, the Gazzino equation of motion doesn't change, but the equation of motion of the fundamental things are psi dagger is equals to minus square root of 2 G V times Ta lambda. These are the equation of motion. You can find the exact solution of these equations, psi. So the exact solution is basically psi is square root of 2 D slash, okay, I should write this as phi classical. So phi classical is basically that whole phi. It's not just V, there are this sigma mu, this x dependence also. This is the classical phi solution of phi. So this is the solution actually. So you can exactly find the solution of this. And then these lambdas are basically the ones which are preserved in the end, which are the Goldsteinos, which still remain the zero modes. These are lambdas are those lambdas. And now what we have to do, the claim is that a linear combination of these fermions, which I will call as chi, which is basically, there is a psi q and psi q dagger, no? So the linear combination, which is psi q plus psi q bar, this linear combination gains mass. That is the claim. And we want to check that claim. So how will one compute the mass? That is the thing we need to compute. So this is nothing but this is just d slash of phi q plus d slash of phi q bar. I don't know why I am always working in the ones which have daggers. So let me write one with the daggers, because otherwise I would have to write d bar. And now look at the solution of the phi above. So the solution, so this solution this is the solution of phi. I have to act d slash on it. And if you take this solution at, there's a x minus x naught here, at x minus x naught being very large, so it far away, if you want to take this solution, you will basically get, you take this x minus x naught out and you do a series, you expand the denominator you will get a constant term. So let me write the series expansion. So basically you will get something like rho square, there is a v over x minus x naught square plus rho square. So rho square over x minus x naught square. So if I just take x minus x naught out, there is a square root here. That x minus x naught will cancel this x minus x naught. Then I have 1 plus rho square over x minus x naught square, which I would expand. So I will get rho square over, there is a half vector. So there is a constant piece. I will get this as phi. So this is very vague. I am.
Maybe what would be useful is if you could outline the logic first before the algebra.
Yeah. So what we are doing is we want to calculate the mass of chi, this operator. So we want to calculate the mass of this operator. So what we will calculate the expectation value chi dagger in the instanton background. So we'll calculate this expectation value. What is this expectation value? This expectation value is this integration over the bosonic zero modes, which were 8 bosonic zero modes for us. The metric which we computed, the determinant of the metric.
What are the locations of your chi dagger?
This is at x and y.
X and
And then there is the multiplication of the fermionic zero modes. You inserted 2 chi's, so there were 2 zero modes, that's why you are computing this expectation value. You have inserted 2 chi's, so this integral I am not writing anymore. And then you have there were actually 6 fermions, no? Approximately 6 zero modes. But the 4 which are lifted, you have to compute their contribution to this thing. The contribution will be basically determinant of this metric. Because if I have to integrate over, let's say, psi 1, psi 2, exponential minus psi m psi, with this psi has component psi 1, psi 2, then you take the square root of m dagger m determinant. No? So this is equal to determinant of m dagger m square root, which is also called Pfaffian. So basically the 4 modes which were approximately zero modes, the integral over those modes will give you factors of v, because there are v's sitting here. So you will basically get some factors of v due to the fermion integral, and then there is the exponential minus s instanton. This is the thing you want to compute, and then there is chi dagger chi.
I'm just saying this once again. You said it very clearly, but I'll just say it just to make sure it's clear. Diksha talked about how at v equals 0, there were 6 fermions. When v is non-zero, but remember we're working with rho much smaller than rho b, very small, so it's non-zero but not very large, effectively. 4 of these fermion zero modes have been lifted.
Yes.
2 remain. So if we're going to do a calculation with one instanton, we're going to get 0 unless we insert 2 fermions. Okay? The 2 fermions are these 2 chi's. We're going to insert these 2 fermions, so we will get something non-zero. Okay. However, so we'll saturate the chi's with the 2 exact zeros. Then, in addition, we're going to have to do the determinant calculation over all the non-zero modes. All the non-zero modes include the genuine non-zero modes, as well as the guys that were fermion zero modes that have become slightly non-zero. Now clearly the determinant gets a larger contribution from the guys that are almost zero modes, because you're doing a calculation like psi a psi, you get
You are doing order by order in V, so that's the leading contribution from
yes, you'll get the most dramatic effects will be these factors of A, which are like very small. Everything else will be order 1 things, corrections to time. Okay? So all Diksha is going to do is to calculate the effect of these 6 zero modes. 2 of them are going to contribute because of the insertions. And the remaining 4 will contribute because they're determined.
Yes. And so basically this is the computation. I can just show you in 2 minutes because it's very late. I can show you in 2 minutes how the powers of it. So the the 4 fermionic zeros, so I have written here 2, there are actually 4, these 4 integrals will give you some power of v, because there are v's there, no, it will give you power of v square. Actually you multiply with m dagger and then you take the determinant, there is a v sitting in all the off diagonal things. You will get a v square power from here. This gave us a power of rho cube. There is an integral over d rho dx naught 4. There is a gauge integral also, which you have to do with a Haar measure, but it's a constant. It's not dependent on rho or something. So this is a determinant which is rho cube. From here you get a v square. This action was exponential minus 8 pi square over g square plus 4 pi square rho square v square over g square. This is what we calculated, the bosonic action. And this chi dagger, what I was computing there was basically chi dagger you can compute from this psi, because chi is a linear combination of psi. Psi is computed by acting this derivative on phi dagger. Phi dagger I was trying to show it goes as 1 over x square. So it's basically a derivative d slash on 1 over x square, which is nothing but fermionic propagator. Fermionic propagator is d slash on 1 over x minus x naught square, no, in the position space. So you get basically 2 fermionic propagators. One is between x minus x naught, the other is between y minus x naught. X and y are the insertion positions and x naught is integrated over. And now this will give you the powers of lambda, because you can use the beta function equation to get g. This we were anyway doing all the time. So this gives you lambda over some other scale mu power 5, because it's 3n minus nf, which is 5 for our case. If you do the rho, then there is a rho integral to be done. If you do the rho integral, basically that will give you 1 over, there is a rho cube exponential rho square, no? Let me see if I have written all the factors.
So each row is effectively 1 over.
Yes. Yes, 1 second, I missed rho square v, 1 rho square v square factor. Which factor? Oh yes. So there, so see in the phi there is a rho square v factor. When I do phi, there is a rho square v factor. Those vectors are also there. So it's rho square v square, because why there is a v square? Oh sorry, rho square v whole thing square, because there are two chi's. So now if you do the rho integral, you will get basically 1 over v power 8, and there was a v power 4 there, and there is a lambda power 5. So you get lambda power 5 v power minus 4. This is what you expected from the. Sorry, I went very over time. So this is how you match the masses. And this you can do for, I did for SUN equal to 2, but you can do with any larger SUN also. And this power counting is easy, because this power counting depends on the number of zero modes. Then it depends on the determinant, this determinant, which will be again n dependent factor. This rho square v is same for any higher n thing also, because you are always inserting 2 chi's. This v square will depend on the dimension of this matrix. So for the, if you have n minus 1 flavors, here we had 1 flavor, that's why v square. If we had n minus 1 flavors, there is a power, n dependent power of v that will come. So it actually matches for every n minus 1, nf is equal to n minus 1 case.
And maybe I'll make one comment.
Yeah.
You know, there's one slightly not, we got a 1 over v. We got the final answer was like 1 over v, which is necessary because we got delta m, affect side delta m to some degree. Right? And you might naively have thought that will never come out. Because you remember our reason. There were 6 0 modes, 2 of which are saturated by explicit insertions. Those were exact 2. So the remaining 4 were approximate 0. Now, if you had an exact 0 mode for a fermion, you get 0. So if you have an approximate 0 mode, you should get almost 0.
Yeah, proportional to V.
So you might have thought you should get factors of V in the numerator. And you do. You get all these various factors of V.
This factors basically. Sorry, these factors. These are coming to do this determinant.
Yeah. But there is one more thing, which is that when you also have to integrate over the size of the instanton. And that integral is controlled by the V squared rho squared in the action. So every factor of rho is like 1 over V.
Yes.
Because what this is saying is that instantons you can integrate, we can integrate them up to the time they become of size 1 over V, and then they stop contributing. So every time you've got a factor of rho, the volume in rho integration space is effectively like 1 over V. And you get lots of factors of rho, and this inverts.
Yeah.
So it's not intuitive that you get 1 over V, and this comes from the integral over the rho moduli.
Yeah. There are effectively 8 powers of rho in. So there's a d rho, there's 3, and there's 4. 8
Yes.
powers. That's why 1 over V8.
And the V to the 4
V to the 4,
there were 4 approximate
0 modes.
0 modes.
So
You
V4.
had V to the 4. But then you had this rho to the 8. That was somehow the key to flipping what you might do.
Yes.
Okay.
Okay. We'll.
Uh,
Hopefully
any-
we'll get
any
lunch.
Any more questions on each side? Okay, then we can thank her very, very much.